Well, now that we understand that there are two mechanisms, we want to give those mechanisms names so that we can refer to them more easily and discuss them more easily. So the first mechanism that we're going to look at, the reaction rate depends on the concentration of both reactants, both the nucleophile and the alkyl halide. So in this case, we've got bromomethane and acetate. We will find that the reaction rate will depend on both of these. And since it depends on both of them, we say that it is bimolecular and it is second order. So we refer to this particular mechanism as SN2, the SN2 mechanism. All right, and that SN2 stands for substitution nucleophilic bimolecular. So SN2 mechanism. The other mechanism, the reaction rate is only going to depend on the concentration of the alkyl halide, and so it's going to be first order. The reaction rate will not depend on the concentration of the nucleophile. And since it's first order, we call it SN1, substitution nucleophilic unimolecular. All right, so those are the two names. We're going to start first with the SN2 mechanism, and then we'll discuss the SN1 mechanism after that. So the SN2 mechanism is a concerted reaction. That means that the carbon-halogen bond breaks at the same time that the carbon-nucleophile bond is formed. In this case, the carbon-bromine bond is breaking at the exact same time that the carbon-oxygen bond is being formed. We'll find that we use curved arrows to indicate bond making and bond breaking, and that they are in the same step. So there's only one step. And that the reaction is bimolecular. That means that the reaction rate depends on both the concentration of our nucleophile and the concentration of our alkyl halide. As you'll see here, rate is equal to K times concentration of methyl bromide times concentration of the acetate anion. All right, so it is bimolecular. So now we want to look at an energy diagram for the SN2 reaction. Since the reaction only has one step, there's only one transition state in the energy diagram. So we'll only see one hump in that energy diagram. Now there's a couple of key features that I want to point out about this energy diagram. First of all, if you look at it, you'll see it's exothermic. Here's our activation energy. There's the energy of our transition state. And here is our transition state species, the transition state as we'll call it. You'll see that in the transition state, we've got a partial carbon-halogen bond, the partial carbon-bromine bond in this case. And we also have the partial carbon-oxygen bond, the bond that's being formed. The other thing that you'll notice is that we have partial negative charges on both the oxygen and the bromine in that transition state. As you can see here, bromine has no charge in the starting material, has a negative charge over here, so partial negative on the bromine. For the oxygen, there's a negative charge on oxygen here, there's no formal charge on the product, the oxygen, and so a partial negative charge on oxygen there. So that would be our transition state. And that's pretty much it for the SN2 reaction. Now, we want to look at the stereochemistry for the SN2 reaction. And the reason we want to do this is because there are two possible directions with which the nucleophile can approach our alkyl halide. One possible approach would be what's called a front side attack. And that's where the nucleophile comes in and approaches from the same side as the leaving group. So here we've got a halogen that is attached to a stereogenic center, this carbon. The carbon has 4 different things attached. And the nucleophile comes in and, in this case, is attacking from the front side. Since it attacks from the front side, then all of this stays the same, and we retain that stereochemistry at that stereogenic center. So we'll make the bond and break the bond at the same time, and we will end up getting this. The other possibility is what's called a backside attack. And this is where the nucleophile approaches from the backside of the molecule. And when that happens, we're going to start forming the bond between the carbon and nucleophile at the same time that we're breaking the bond between the carbon and the halogen. And when that occurs, we'll find that we change the stereogenic center. So there's a change in that stereogenic center, and that is the backside attack. So if we don't know which one of these is going to occur, then all we have to do is do a reaction and see which one of these we get. And if we get this one, it must be that we had a front side attack. And if we get this one, it must mean that we had the backside attack. So the front side and the back side give enantiomers. The front side would give the original configuration, and the back side would give the inverted configuration. And so here is what we would get if we had the front side attack. We would retain that configuration at the stereogenic center. And here is what we would get with the backside attack, and we would get inverted stereochemistry at that stereogenic center. Well, when we do the experiment with SN2, we will find that we always get the inverted stereochemistry. We don't get any of the retained stereochemistry. And the rationale behind this is that in order for it to do front side attack, you would have to have the electron-rich nucleophile come in and be on the same side as the electron-rich leaving group. And that's just not very favorable. So we'll find that all SN2 reactions are going to proceed by backside attack, not by the front side attack. So now let's look at the transition state of an SN2 reaction. Now that we know for sure that it is a backside attack, it's concerted, let's look at the transition state. The transition state is always going to have partial bonds to the nucleophile and the leaving group. So here we'll have, we're forming a bond between the carbon and the nucleophile. We're breaking the bond between the carbon and the bromine. So we'll have partial bonds between carbon and nucleophile, carbon and bromine. And then we'll also have partial charges. If the nucleophile is negative, then we'll have a partial negative on the nucleophile. And then with halogen, we're always going to have a negative halide as one of our byproducts. And so therefore, we will have a partial negative charge on the halogen in the transition state. So that's what our transition state is going to look like. So the nucleophile and the bromine will be exactly opposite each other. If you look at these models down here, the ball and stick models, you can see how the stereogenic center kind of flips around when the nucleophile comes in. And again, that's because in SN2, we always get that backside attack, which causes inversion of the stereochemistry. So here are a couple of examples of SN2 inversion. We've got this iodobutane here, and when the nucleophile comes in, it will invert the stereochemistry on that carbon 2, and so we will end up getting this particular enantiomer instead. So we'll get the inversion product. And then here, when the nucleophile comes in and attacks carbon 2, we will get inversion of the stereochemistry at that carbon as well. So anytime we've got an SN2 mechanism, we are going to get inversion. So we're going to look at number 61. And if you're looking at your in-class assignment, you'll see that the next one is number 58. We'll go to the next page after that, and we're going to do 61, and then we're going to go back to 58. So in case you're wondering, that's what happened there. All right, so draw the products of each SN2 reaction and indicate the stereochemistry where appropriate. So the first thing we want to do is we want to see, is the halogen at a stereogenic center? And we'll see that this carbon has 4 different things attached, so it definitely that definitely is a stereogenic center. So we're going to get inversion of that stereogenic center. Now, the easiest way to do this is to leave these 2 things exactly in the same place, and then flip that deuterium back and have the OCH3 come forward. So CH3 carbon hydrogen. So we're going to leave those 2 in place. And then our wedge is going to be our nucleophile in this case, so OCH3. And then our dashed line is going to be that deuterium. And then, let's see, plus our halogen, halide there, so chloride would be our product. And as I mentioned, the important feature of this is that we got inversion at this stereogenic center. So I'm going to put inversion. All right, so we got inversion at that stereogenic center. Now on this next one, this one's a little easier because we don't have any stereogenic centers to worry about. We've got this primary alkyl iodide, and so the hydroxide ion comes in and it is going to replace that iodine with OH. So 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons, and then OH, and then we will have iodide. All right, and again, since there's no stereogenic center to worry about, then drawing the product is really, really easy. On this next one, you'll see that we do have a stereogenic center, but you'll notice that that stereogenic center isn't where the halogen is. The halogen is at this primary carbon that's down here at the end, and so we're not going to invert this stereogenic center, and this one isn't a stereogenic center, so we will have this particular stereogenic center retained, and this is just going to be replaced with our product. So 1, 2, 3, 4, 5. So those are those 5 carbons. We'll go ahead and put that wedge for the methyl group there, and that hydrogen, it's going to stay where it is. And then we'll have OCH2 CH3. So O CH2 CH3, and I'll just draw it like that because that's an ethyl group. All right, so again, notice that it doesn't affect the stereogenic center because the reaction is not occurring at that stereogenic center. And then our other thing would be the chloride. All right, for part D, we've got 2 stereogenic centers, and so this is kind of like a combination of both A and C. In A, we had a reaction at the stereogenic center, and at C, we had a reaction that was away from the stereogenic center. So what we're going to find is that it will only invert the stereochemistry at the carbon where the halogen is. So we'll only change that stereochemistry. This one is going to remain the same. So as far as drawing that, all right, so since bromide is coming forward, we will end up with, so cyanide is our nucleophile, we'll end up with this as our product. So we'll get that as our product. And then, of course, our halide is Br minus. Our halide is Br minus. Okay, so that's how we deal with stereochemistry. We will see more stereochemistry things as we go forward. Now let's look at the rate trend for the SN2 reactions. And we're going to look at methyl, primary, secondary, and tertiary alkyl halides. We're going to find that the less substituted the alkyl halide is, the faster the reaction goes. So as the number of R groups increases, the reaction will go slower. And as the number decreases, the reaction rate will increase. So we'll find that for SN2 reactions, methyl goes really, really fast. Primary goes pretty darn fast. So methyl and primary alkyl halides will go relatively fast compared to the other alkyl halides. Secondary is going to be much slower. And then the tertiary alkyl halide is going to go so slow as to say that it doesn't really go at all, so that we don't get SN2 reactions on tertiary alkyl halides. They're just too slow for that to work. All right, so methyl and primary, fast. Secondary, slow. Tertiary, just doesn't happen. It's too slow to even measure. And in fact, other reactions will occur rather than the tertiary alkyl halide going by SN2. So next we want to look at steric effects. We want to explain this using steric effects for the SN2 mechanism. So if we look at the electrostatic potential maps, it can illustrate the steric effects, the steric hindrance at the carbon around the steric hindrance at that carbon where the nucleophile is trying to approach. With hydrogens, those hydrogens are relatively small, and so the nucleophile is able to come in really easily and attack that carbon, and therefore this goes pretty fast. With primary, the nucleophile is still able to come in. There's still lots of accessibility to do that backside attack, but it is a little bit slower than the methyl. For secondary, it slows down pretty substantially because there's just less of a pathway for that nucleophile to come in. It's still technically possible, but it's much, much slower. And for tertiary, this ends up being so crowded that the nucleophile just isn't capable of attacking that carbon. So again, methyl and primary go really fast, secondary relatively slow, and tertiary so slow as to not really happen. So now let's look at the SN2 transition state and use that to help us explain the relative rates of methyl, primary, secondary, and tertiary alkyl halides. Here we've got a methyl alkyl halide, and if we look at the transition state, you'll see that we've got these three hydrogens that are all coplanar with the carbon in the transition state. And so it's not a very crowded transition state. Those hydrogens don't take up much space, and so they're not bumping into each other. There's no steric interaction in that transition state. We're going to look at the secondary alkyl halide substitution, SN2. If we were to do tertiary, that would be drawing something that really doesn't happen, so we're not going to do tertiary. We're just going to look at the secondary. And you'll see that in the secondary alkyl halide, the transition state for it on SN2, that it's a much more crowded transition state, and so these methyl groups are sterically hindering access to the nucleophile to get in there, and so this is just higher energy. Since it's higher energy, that means the transition state will be higher and the activation energy will be higher, and that will slow down the reaction. So secondary alkyl halides go much slower than methyl or primary. And then the tertiary would be so crowded as to not make a favorable transition state at all. So next we want to look at SN2 steric effects on the activation energy. So here we've got the methyl halide, so the methyl bromide, and we'll see that here is our transition state. It's relatively low. This doesn't really mean anything unless we put it next to our secondary alkyl halide and its transition state. You'll see that the transition state is higher in energy than the transition state for the methyl, and that gives it a larger activation energy, which means this reaction will go much slower. So the more substituted, the higher that transition state energy, and the larger the activation energy is going to be. So let's look at the overall summary for the SN2 mechanism. So since it's SN2, the 2 means that it's second order. So we'll have a second order rate law, and it will be dependent on the concentration of the alkyl halide and on the concentration of the nucleophile. The mechanism is concerted, so it is a one-step mechanism. We do get backside attack, which causes inversion of configuration at the stereogenic center if your halogen is at that stereogenic center. Remember, it doesn't change the configuration, the stereochemistry configuration, at other locations. It only affects it at the stereogenic center. And then the identity of the alkyl halide, methyl and primary go really fast, secondary goes much slower, and tertiary goes so slow as to say we just can't really do it with tertiary. So let's look at number 58. Here you're going to have to go back one page to look at number 58. All right. So first thing here, we want to draw the mechanism using using the curved arrows. Since it's a one-step reaction, we will have to have 2 arrows in that first part. 1, 2, 3, 4, 5. And I'm redrawing this because it's hard to do all that up here. Plus, I'm going to go ahead and I'm going to draw what the cyanide ion looks like. There's a negative charge on that carbon. All right. And we'll find that we're going to make the bond between this carbon and that carbon simultaneously as we break the bond between this carbon and halogen. So we're making a bond between carbon and carbon, and we're breaking the bond here at the same time. And then our products are here. 1, 2. And then bromide. All right, so there we go. Draw an energy diagram. So since it's a one-step reaction, we're going to have one transition state. All right, so draw an energy diagram. We want to label the axes. So we're going to put reaction coordinate here. And then here, we're just going to be kind of generic and put energy. All right, so the reactants, the products, and the activation energy. And then here it says, assume the reaction is exothermic. So if the reaction is exothermic, then here is our reactant, and our product is going to be lower in energy. So there you'll see that the product is lower in energy. And then this is our transition state, is right there. So label the reactants, products. Our activation energy is going to be the difference in energy between our reactant and our transition state. And so this will be our activation energy. And I'll go ahead and draw that in red. That is our activation energy. Our delta H is going to be the difference between the energies of the reactant and the product. And since it's going down, our delta H here would be negative. All right, so there is our delta H. So we've got everything. So our axes, the reactant, the product, there's our transition state. Our activation energy is the difference between the reactant and the transition state, and the delta H is the difference between reactant and the product. So next, draw the structure of the transition state, and this is where we want to have our partial broken bonds and partially formed bonds. So draw all the bonds that are present both before and after first. So 1, 2, 3, 4, 5, all of those carbons are present. And we're going to have a partial bond between carbon and bromine. And we'll have a partial bond between carbon and the cyanide. So C, N. All right, so there's a partial bond there and a partial bond there. Here, bromine has no charge. Here, bromine has a negative charge. So we're going to put a partial negative charge on that bromine. Same thing with the carbon. Here, carbon has a negative charge. Over here, carbon has no formal charge, so we'll put a partial negative charge on that carbon as well. All right, so we've done partial bonds, we've done partial charges. Now we want to put it in a bracket. And then finally, we want to label it with the double dagger to indicate that it is a transition state. All right. Well, the next thing that we want to do here is to write the rate equation. So I suppose here I can say this was A, this was B, this was C, and now D. We want to write the rate equation. And the rate equation, since it is SN2, it's second order, then the rate here is going to depend on depend on the concentration of both the alkyl halide and the nucleophile. So we'll say that the rate, scoot that up a little bit, the rate is equal to the rate constant K times the concentration of our alkyl bromide, which I'm just going to put R and then Br because it's a bromide, times the concentration of the cyanide ion. And so those are both first order with respect to each of those and second order overall, and again, second order SN2. All right, what happens to the reaction rate in each of the following instances? The leaving group is changed from bromide to iodide. Well, if we change it from bromide to iodide, we're improving the leaving group, and anytime you improve the leaving group, you're going to increase the rate of reaction. So we'll find that for part E, and I'll go ahead and number that 1. All right, so if you improve the leaving group, you will increase the rate of reaction. We'll find the same thing when we look at the other mechanism, which is the SN1 mechanism. Pull that out a little bit. All right, sorry about that, moving around so much. Okay, so now let's look at our second thing here. Our second thing is the solvent is changed from acetone to ethanol. Now, we haven't talked about the solvent effects just yet. And since we haven't talked about the solvent effects, I could skip this, but I'm going to go ahead and tell you that for SN2, and this is an SN2 mechanism, for SN2, it is favored by a polar aprotic solvent, like acetone. So it's favored by polar aprotic. When you change the solvent to polar protic, you will end up decreasing the rate. So in this case, ethanol is polar protic. All right, so polar protic will slow SN2. And we'll talk about that in more detail here in just a bit. All right, trying to keep that all in focus there. All right, for the third one, the third one says the alkyl halide is changed from CH3, CH2, 4Br, which is our starting material. It's changed from that to this, which is a secondary alkyl halide. All right. Well, changing it to a secondary alkyl halide would decrease the rate. Because the secondary is going to go slower than a primary. So secondary is slower than a primary. And this is for SN2. For SN1, we'll find that it goes the other way. So, all right, for number 4, the concentration of cyanide is increased by a factor of 5. Well, if we increase the concentration of cyanide by a factor of 5, then the rate should go up by a factor of 5. So that will increase the rate by a factor of 5. All right, for 5 it says the concentration of both the alkyl halide and the cyanide are increased by a factor of 5. Well, if you increase this by a factor of 5 and this by a factor of 5, you're going to increase the rate by 5 times 5, so you'll increase it by a factor of 25. So we'll increase it by a factor of 25, and that is a pretty significant increase. All right, so now that we've done the SN2 mechanism, we want to look at the SN1 mechanism. All right, so we want to look at that SN1 mechanism. So the SN1 mechanism has 2 steps. In the first step, we break the carbon-halogen bond, and in the second step, we form the carbon nucleophile bond. So our first step we will find will always be the slow step in an SN1 mechanism. So we're going to break that carbon-halogen bond in that first slow step. We will form a carbocation intermediate. Now, I think we've briefly mentioned carbocations before, but we're going to talk about them a lot more in this chapter. All right, and then in a slow second step, we will make a new bond between carbon and the nucleophile. You'll see that the curved arrows indicate that there's just one thing happening in each step, a bond breaking in the first step, and the bond making is in a subsequent step. We'll find that since the rate of reaction only depends on the rate determining step, the slow step, and that slow step is this first step, that the reaction is unimolecular because there's only one molecule involved in that step. So we'll find that the rate is equal to K times the concentration of the alkyl halide. We'll find that the identity and the concentration of the nucleophile will have little to no effect on the reaction rate. In principle, it should have 0 effect on the reaction rate. So changing that to a different nucleophile shouldn't affect the rate, and changing the concentration of that nucleophile shouldn't affect the rate either. All right, we now want to look at an energy diagram for the SN1 reaction. Since there are 2 steps, that means we will have 2 transition states in the mechanism. And with 2 transition states, that means two humps in the mechanism, 2 humps in the reaction coordinate diagram. So here is our reactant, here is our product over here. Our first step, we're breaking that bond in between. We're breaking that bond in between the carbon and the halogen. We form a carbocation intermediate, and again, we're going to talk extensively about that carbocation intermediate. And then we're going to form a new bond in between the carbocation and the nucleophile, and then we'll get our product as our final thing down here. In our first transition state, we do have a partial carbon-halogen bond, and we'll get partial charges on the carbon and on the halogen. In the second step, we'll have a partial bond between carbon and oxygen as that one is being formed. Again, partial charge on the carbon and also on the nucleophile atom. And then here you'll see the partial negative charges on the oxygen and the bromine, as I just mentioned a minute ago. Now, other things that I want to point out about this is that the rate determining step is going to have the largest activation energy. You'll see that there is a large activation energy between our starting material and our first transition state. And so that is going to be our rate determining step. When you look at the second step, that activation energy is much smaller, and so that reaction goes much faster. kind of like when you are going, you're on a roller coaster at an amusement park. Usually that first hill is the large one, and it takes a while to get up to the top of it, and then everything after that goes pretty quickly. So you have enough energy here that you go through this transition state really easily. And then finally, the other thing I want to point out is this particular reaction is exothermic, and we'll usually find that they're exothermic, but sometimes they can be, delta H can be close to 0. It can even be slightly endothermic if you play tricks with it. All right, yes, and so there the rate determining step is our first step. So we now want to look at stereochemistry for SN1 reactions. We saw that for SN2 reactions that the stereochemistry was inverted. Well, when we do an SN1 reaction, we get a carbocation intermediate. That carbocation intermediate is sp2 hybridized, and so therefore it is not a stereogenic center. So if you started off with a stereogenic center and you form a carbocation, you've lost that stereogenic center. So any stereochemistry that your starting material had at the halogen carbon will be lost. Now, any stereochemistry at other carbons is going to be retained because it only affects that one carbon. So if you had another stereogenic center somewhere else, then that would not affect the stereochemistry. This would not affect the stereochemistry there. We'll see an example of that here in a bit. So because we generate that planar carbocation, and that planar carbocation is achiral, that means that the nucleophile, when it comes in, it can come in from either side. If it comes in from the front, we will end up getting this particular enantiomer, and if it comes in from the back, we'll get this one. Well, because this is achiral, both of those approaches are equally likely, and so we should get a 50-50 mixture of these two enantiomers. When we get a 50-50 mixture of two enantiomers, we call that a racemic mixture. Now, we talked about racemic mixtures before. The process of taking a stereogenic center and turning it into a racemic mixture is called racemization. So that process is called racemization. In SN2, we don't get racemization. In SN1, we do. And that is one of the big differences between the SN1 and the SN2 reactions, as far as how useful it is. So here are a couple of examples of racemization in the SN1 reaction. So here we've got, looks like we've got, 4 different things attached to this particular carbon. And then we would form a carbocation, and we would get 2 different potential products here when we form the alcohol. And so we would get a racemic mixture. Same thing with this tertiary chloride. We would get a racemic mixture there as well. Now, just as a reminder, here we've got a neutral nucleophile, and with a neutral nucleophile, we would temporarily form an H2O H2O plus as our new substituent, but a subsequent and very quick step would come along and deprotonate that to give us the alcohol. We did this a little bit back in section 6 of this chapter. So now for the rate trends for SN2 reactions, or SN1 reactions rather. So we're going to look at methyl, primary, secondary, and tertiary, and we'll find that it is exactly the opposite that we had for SN2. For SN1, as you increase the number of alkyl groups on the carbon, it will increase the rate of the reaction in an SN1 mechanism. So we'll find that tertiary alkyl halides undergo SN2 reactions quite rapidly. So it's a very fast SN2 reaction. Secondary alkyl halides react much more slowly. So we'll get a substantially slower reaction for the SN1 on a secondary alkyl halide. Primary and methyl alkyl halides, they go so slow as to not really undergo SN1 reactions. And so, again, this is exactly the opposite trend that we had for the SN2 reactions. We'll find that the nature of the alkyl halide turns out to be the most important factor in determining whether a reaction is going to undergo a primary or undergo an SN1 or an SN2. And we'll discuss that a little bit more when we're comparing them here a little bit later. So here is the summary of the SN1 mechanism. First of all, reaction kinetics, it's first order, as the number 1 implies, and that it depends on the concentration of that alkyl halide. The second step, there are 2 steps in the reaction. The first step is rate determining, and the second step is quite fast. The stereochemistry, if you have a stereogenic center at where the leaving group is, you're going to get racemization at that stereogenic center. And then the identity of the alkyl halide, the more substituted the alkyl halide, the faster the reaction goes. So let's look at number 65 on the in-class assignment. Okay. And we will draw a mechanism for this reaction using the curved arrows. So our first step we're going to break the bond between the carbon and the halogen. So we're going to break that bond between carbon and iodine. And that's going to give us CH3 carbon, CH3 plus iodide. And we will have a carbocation there. We're going to talk about that carbocation extensively here a little bit later. All right, so there's our carbocation. And then in a subsequent step, we have H2O, and it has a lone pair of electrons, and that lone pair of electrons is going to attack that carbon, and we'll end up with this. Now, I'm going to draw it out so that you can see that there is a there's a positive charge on the oxygen in that product. Now, one other thing that you'll see if you go back and look at that section 6 on the in this chapter, in section 6 we talked about when we have a neutral nucleophile like this, that we end up deprotonating in a subsequent very fast step. So this would get deprotonated by other water molecules that are present in the mixture. So it just come along, deprotonate that, and we would end up getting an alcohol instead of this positively charged product. All right, that aside, that's that. So you'll notice that the bond breaking and the bond making occur in different steps. Our first step is the rate determining step, and it is the slow step. So now draw an energy diagram. We'll label the axes, the starting material, product, EA, delta H, and assume that the starting material and product are equal in energy. So let's do our diagram here. And we're going to call this part A and part B. So that is the energy, and this, of course, is our reaction coordinate. So that is our reaction coordinate. Since there are 2 steps in this reaction, that means that we will have 2 transition states. And so let's go ahead and we'll put reaction down here, or reactant down here. Product is going to be equal in energy because it said assume that they are equal in energy. And then in our first step, We'll have a significantly large transition state, high transition state. We'll have an intermediate, and then we'll have a subsequent bond formation step, and then there's our product. And then we'll label this as I, our intermediate, not to be confused with I, our iodide. Intermediate here is that carbocation. Okay, so we've labeled the axes. We've got starting material, which is reactant, intermediate, there's our product. We want our activation energy, and the activation energy, well, there's two activation energies, but we're interested in the first one. Let's go ahead and we'll call this transition state 1 and transition state 2. Because there's two steps, that means there are two transition states. And the difference between our reactant and transition state 1, that is going to be the activation energy for the overall reaction. We're going to call that EA1, but that's also the activation energy overall. For our second step, so we start here. This is going to be the activation energy 2. And activation energy 2, because it's such a small activation energy, that's going to be a pretty fast reaction. All right, and then delta H here, since the reactant and product are approximately equal, delta H is approximately equal to 0. So this is neither an exothermic nor endothermic reaction. All right, delta H. Assume that the starting material and the product are equal in energy. We did that. And then there's one other thing that I want to point out is that the first step, the one that's rate determining, is endothermic, and the second step is exothermic. So first step is endothermic, and the second step is exothermic. All right. So part C, draw the structure of any transition states. So we have two transition states, and we'll want to indicate both of them. So CH3, carbon, CH3, CH2, CH3. And here we're breaking the bond between carbon and iodine. So we're going to put a partial bond in between carbon and iodine. And then here carbon has no charge, but there it has a positive charge. So we're going to put a partial positive charge on the carbon in the transition state. For iodine, it has no charge here. It's negative there. So we're going to have a partial negative charge on the iodine. Okay. And so we've done the partial bonds, the partial charges, and we put the brackets around it, and now we'll put a double dagger, and I'm going to put a 1 to indicate that it's transition state 1. All right, for transition state 2, here we're forming a bond between carbon and oxygen. So we're going to have this, but it'll have a partial bond there. So CH3, carbon, all right. When we look at this, we'll see that we have a positive charge on the carbon and no charge on the carbon there. So this should be partial positive on the carbon. And then on the oxygen, here the oxygen's neutral, but there it's positive. So we'll also have a partial positive. That should be a delta there. A partial positive on the oxygen there as well. Now, as I mentioned, there is a subsequent step where we deprotonate. We're not drawing that step out, but there is a subsequent step where another water molecule would come along and deprotonate this and give us an alcohol. But that we're not specifying that in this particular problem. Okay, so that was C. D, what is the rate equation for this reaction? Well, the rate equation is only going to depend on reactants that are in the rate determining step. Since our rate determining step is this slow first step, and the only reactant that's there is the alkyl halide, then we will find that the rate is going to be equal to K times the concentration of that alkyl halide, and we'll indicate that it is an iodide there. So it's going to be first order for that. So that is part D. And now for part E, we'll go through and look at these steps. So what happens to the reaction rate in each of the following instances? The leaving group is changed from iodide to chloride. Well, iodide's a much better leaving group than chloride, so this is going to decrease the rate of the reaction. All right, so chloride is not as good of a leaving group as iodide. Question 2 here, the solvent is changed from H2O to DMF. And so again, we will find that polar protic solvents tend to favor SN1. DMF is a polar aprotic, so this would decrease the rate of the reaction. Because because polar aprotic does not favor SN1. Polar aprotic favors SN2. And sorry about it being all the way down at the bottom there. All right. And then on the third part of this, the alkyl halide, and you just get back up here, the alkyl halide is changed from CH3 CH2CH3, so that's the tertiary alkyl halide, that one, to CH3 CH, so that's a secondary alkyl halide. All right, so because it's changing to a secondary alkyl halide, it's going to slow down the rate. So it will decrease the reaction rate because secondary is slower than tertiary for SN1. All right, our fourth thing here, the concentration of H2O is increased by a factor of 5. Well, if we look at the rate law, since H2O is not in the rate law, we will find this will have no effect. So no effect on rate because H2O is not in the rate law. All right, no effect because H2O is not in the rate law. And then finally, on number 5, the concentrations of both the alkyl halide and water are increased by a factor of 5. Well, if you increase the water, it has no effect, but the alkyl halide, it should increase by a factor of 5. So all right, so increases by a factor of 5. Okay, so before we go to the next section, we're going to stop this video. We're going to stop this video and we'll pick up with another video for for the next section where we're going to talk about carbocations.